In this video, I'm going to go through the work, power, energy, and momentum test information. First kind of problem you may see is where you have a weight over here, and it's going to be a certain distance away from this fulcrum. So here's your distance right there, and you're going to have another weight over here, and it's going to be a certain distance. So the equation that comes from that is F1 D1 equals F2 D2. So F1 D1 equals F2 D2. F1 was 200 newtons, and it's 4 meters away. So 200 newtons, 4 meters away, and that's going to equal to this 400 newtons. And it's asking us how far from the fulcrum it's going to have to. So how far away from this pivot point does that have to be located? So you get D2 equals 200 times 4, and that divided by 400. So 200 times 4 divided by 400, and that's going to be 2 meters away. And so it kind of makes sense, double the mass, half the distance, and they'll have equal torque on the other side, and it's going to balance off this teeter-totter or seesaw, or whatever you want to call it. Next kind of problem, you have 9,000 joules of work, so W equals 9,000 joules, and 50 seconds, time equals 50 seconds. What's her power output? So she's climbing the stairs, so she's lifting up. Well, it doesn't really tell her if that's her weight or what it is, but you're going to be doing that 9,000 joules of work over that time period. And on the equation sheet, power equals work over time. Work is 9,000, time is 50. So 9,000 divided by 50 ends up being 180. So 180 in watts is the unit for power. Next one, 1 kilogram rock is dropped from a 20-meter high cliff. What's kinetic energy instant before it hits the ground? So this is a before-after situation. So you're going to have a rock, and it's going to be dropped from a 20-meter high cliff. And so what I'm just going to do is I'm going to give some information. H initial is going to be 20 meters. The rock has a mass of 1.0 kilograms. And what you're asked for is this final part. So this is at the beginning. You're asked for the velocity final at the very end right here when it gets to the bottom. So the velocity initial is going to be 0. And also the height final is going to be 0 because you're going to be on the ground at this point in time. So you're going all the way from up here to down here, and you're still going to have the same mass. It's still going to be the 1.0 kilogram mass. And so the equation you got to think about is the conservation of energy equation. So all the PE plus all the KE initial equals all the potential energy final plus the kinetic energy final. And so I'll just rewrite that equation over here. PE initial plus KE initial equals PE final plus KE final. And I'm going to break it down even more. PE is gravitational potential energy equals, so it's PE is mgh, and the kinetic energy is 1/2 mv squared. So breaking this down, mgh initial plus 1/2 mv squared initial equals mgh final plus 1/2 mv squared final. And now you just plug it in values. So the initial mass was 1 kilogram. Gravity will go with 10. The initial height was 20 meters plus 1/2 times 1 times 0 squared. So this is going to be canceled out. Equals the mass still 1, but the height now is 0. And then just going with that equation, that would have been 10 because that was the gravity part. 10, the height now is 0. Plus 1/2, m is still 1, and then vf squared, this is what we're trying to find. So we'll go ahead and plug this all in. 20 times 10 is going to be 200 equals, this is going to cancel out, 1/2 times 1 times vf squared. We're going to multiply both sides by 2 to get rid of that, so by 2. Then you're going to have vf squared equals 400. And we're going to take the square root of both of those. So VF equals 400, square root of 400. And that ends up being 20 meters per second. So that's how fast it would be going when it went to the when it hit the ground. 100 kilogram cart accelerates from 5 meters to 10 meters compared to the cart's final kinetic energy to its initial kinetic energy. So two ways to go about this. You can do either rule of ones or you can just plug everything in, just plug and chug. So I'll go ahead and do rule of 1 second because that's actually easier to do, but you have to understand how to approach it. And so the equation is Ke equals 1/2 mv squared. And if I'm just plugging in values, 1/2 times the mass was, let's write down all that information. Mass was 100 kilograms. The VI, or the velocity initial, was 5 meters per second. The final velocity was 10 meters per second, but we're not going to really, we're going to just be plugging these in individually. So we're just going to plug these in this equation. So 1/2 times, let's do the 5. 1/2 times the 100 times the 5 squared. And that would be, so 0.5 times 100 times 5 squared, and you get 1250 joules of energy. And then I can do the same thing. So that's the 5. Do the same thing with the 10. When I do that, 0.5 times 100 times 10 squared, I get 5,000. And to go from 1250 to 5,000, that would be 5,000 divided by 1250, which equals 5,000 divided by 1250 equals 4 times. So that's one approach. So one way. And here's another. So we're going to go off the same equation, Ke equals 1/2 mv squared, but we're going to go ahead and we'll take the equivalent. We're going to do rule of ones. I'll erase this over here because rule of ones is going to be over here. And so I'm going to just put 1/2 mv squared over 1/2 mv squared. This is going to be the new. This is going to be the old. And what I'm going to say is, well, going from 5 meters per second to 10 meters per second is 2 times. So V equals, and I've been writing it out like this, 2 times. And so I'm just going to plug in, that's going to be my V over here. And so we're going to just go ahead and we'll plug everything in. 1/2 times 1, the mass is the same, 2 squared, and over 1/2 times 1 times 1 squared. And when I do that, that right there is going to be equal to 4 times. So either way you can get to the right answer. Okay, potential energy depends on PE equals 2 ways to get PE. You can either do the work, which is going to be the force times distance, or work equals force times distance. So it's how much force is applied over a distance. It could be the weight times distance if it's a gravitational potential energy. And so GPE, the GPE equals mass times gravity times height. Or the simpler version would be, if you're given a weight, it'd be weight times the height. Or GPE, gravitational potential energy, is mass times gravity times height. All these have a location, which is distance, or it's going to be either distance or height, which is just a distance. Some sort of distance. And that's why it's related. That's why it's location. Okay, next one. 20 Newton force is used to push a 2.0 kilogram cart across a frictionless surface for a distance of 5 meters. What's work done on the cart? So work equals force times distance. We have a weight. No, just a force equals 20.0 newtons, and you're pushing a mass of 2.0 kilograms. And you're pushing at a distance of 5 meters. And so what's the work done on the cart? Work equals force, which was 20, times distance, which was 5. And you would get, so 5 times 20, and you get 100. So 100 joules of work. Next one, Marshall has found an empty swimming pool that he's trying to skateboard in. Now, a diagram above is a cross section of the swimming pool. It labels with different labels on several points along Marshall's path. At what point does Marshall have the greatest potential energy? So what you're looking for is the highest point. Key height is going to be so we want the highest point, and that is going to be right here. So Marshall would have went boom and went all over here, and he would have ended right there. Well, this is going to be the highest, and so that's going to be A. Okay, next one. Describe potential energy and kinetic energy at each point position for the skater. So this was going to be the maximum potential energy, max PE. We can say, let's say, go ahead and say gravitational potential energy. And it's going to be the least kinetic energy because it's stored. And then we go from here all the way down there, and this is where we're going to have the least GPE because we're the closest to the ground, and we have the most kinetic energy. But then he would start to lose as he's going back up. What's happening on the way up? GPE would be going up as KE is going down. So if you're describing C, you're going to have more gravitational potential energy, less kinetic energy. Even more gravitational potential energy and less kinetic energy, but definitely not as much as this point over here. So all these positions right here, C and D, that's what's happening. So B has a point specific value, but C is just on the way back up. Okay, a student applies 20 newtons of force horizontally, so force is 20.0 newtons to move a crate a distance of 24 meters. How much work is done by the student? So here's another work equation. Work equals force times distance. 20 times 24, and you get 480 joules. Rock with a mass of 3 kilograms is thrown straight up in the air. Find the change in gravitational potential energy of the rock as it goes from the ground to 5 meters above the ground. So right here, GPE would have been mass times gravity times height. That would have been 3 times 10 times 0. So that's going to be 0. And then as you get to the top, GPE equals mass times gravity times height. And this time it's going to be the mass of 3 kilograms, gravity 10, and then the height of 5. And so we get 30 times, so we get 150 right there. So 3 times 10 times 50, so times 5 was 150, and that's going to be joules. And so this is the change between there and there. It's going to be 150 joules. Let's make sure, yes. Okay, a 5 kilogram car is pushed from rest at the top of a 5 meter high hill. What was the car's kinetic energy at the bottom of the hill? Ignore friction. Okay, so we have, we're looking for what the kinetic energy. So, okay, so we're going for PE initial plus KE initial equals PE final plus KE final. And they're asking you for kinetic energy at the bottom of the hill. And they're telling you information about this right here. So I'm going to break this one out. MGH initial plus 1/2 mv squared equals MGH final plus, I'm just going to leave this as KE final because this is what the question is asking you for. So 5 kilogram cart is pushed from rest at the top. So when we're thinking about our givens, our VI equals 0, so our initial velocity. Our height initial was 5 meters. The mass was 5 kilograms. Here they're saying the bottom of the hill. So thinking about our final information, our VF equals unknown. That's what we're trying to, or no, we're not concerned with that. Question doesn't ask that at all. It asks for the final kinetic energy at the bottom of the hill. So the bottom of the hill, the height final is going to be 0. And this is all information we have, and this is all information we need. Let's plug it in. Mass is 5. Gravity is 10. Height is 5. Plus 1/2 times the 5 kilograms times the velocity, which is 0, so that's going to cancel out, equals the mass was 5, the gravity was 10, the height was 0, plus KE final. So that cancels out because of that, that cancels out because of that. So all we have to do now is figure out what this is, and that's going to be equal to the KE final. So 5 times 10 times 5 equals 250 joules equals KE final. And so this was the PE initial equaled the KE final. So once again, I just took this equation and used it how I needed to, and this is what happened. Describe a situation where there would be a decrease in potential energy. Decrease in potential energy would be if you were going down. Going downwards, your PE, specifically gravitational PE, is getting smaller. Okay, so that's the situation. Any sort of going down would be that. Would increase in KE, so KE equals 1/2 mv squared. I probably should do that over here. So remember, GPE equals mgh. So if you were going down, that was getting smaller. The overall is getting, this is getting smaller. Okay, back to this, the velocity. So if you were slowing down, any sort of slowing down right here, if you have that v was going down, then you're going to have actually not slowing down, that's going to be increasing. So I should have read this. You're looking for an increase, so speeding up, not slowing down for this problem. Okay, if both mass and velocity of an object are doubled, what happens to kinetic energy? So back to rule of ones, whatever you want to call it. KE equals 1/2 mv squared, and we go ahead and do a ratio. So new to old, and the mass is 2 times, and the velocity is 2 times. What happens to kinetic energy? KE equals question mark. So we've set this up, set the equation up twice. The new equation would be 1/2 mv squared new over 1/2 mv squared old. So 1/2 times the mass is 2 times the velocity is 2 times squared. Only the velocity is squared over 1/2 times 1 squared. And so when you plug that in, so it's 0.5 times 2 squared equals 4, but then you have to divide it by 1/2. And so it ends up being 8. So 8 times right there. Write that a little bit better. That becomes that. And there's your answer. Okay, what's the kinetic energy of a 0.14 kilogram ball thrown at 30 meters per second? So KE equals 1/2 mv squared. The mass is 0.14 kilograms. The velocity is 30 meters per second. We plug all that in. KE equals 1/2 times 0.14 times the 30 squared. And so we get 30 squared equals 900 times 0.14 equals 126 times 0.5 equals 6363, and that would be joules of kinetic energy. Okay, 2.5 kilogram toy falls from a height of 7. Before hitting the ground, what's its speed? So we're going to have the PE plus KE, and that's going to be equal to the PE plus the KE after, and here we're going to break everything down. So these are all initials, these are all finals. Break everything down to its equation that makes it up. Once again, GPE or PE equals mgh, and KE equals 1/2 mv squared. So we plug in our mgh initial plus 1/2 mv squared initial equals mgh final plus 1/2 mv squared final. And all our information we have is, we'll go ahead and make a givens list. The toy falls from a height, so the mass is 2.5 kilograms. The height initial is 7.0 meters. And height final equals 0 because it's going to be on the ground. At that moment, right before it gets to that point, what was its velocity? It's saying it's falling. It doesn't say anything else. So we're going to assume that it's starting at rest. And now we have all our information to plug into the equation. So 2.5 kilograms times the 10 gravity times the height, which was 7, plus 1/2 times the mass 2.5 times the 0 squared, so it's going to cancel itself out, times the mass, once again 2.5. You got your 10, but you're now on the ground, which is 0, so that cancels that out, and you get 1/2 mv squared. Well, m was the 2.5, and we are trying to solve for VF squared. So we're trying to find this thing right here. So let's go ahead and plug everything in. 2.5 times the 10 times the 7 equals, so we get 175 equals, and then just 0.5 times 2.5 equals 1.25, and that's going to be VF squared. Well, now we want to go ahead and we need to get rid of that. So we're going to have VF equals 175 over 1.25, and we're going to take the square root of that because we need to break that squared away from it. So 175 divided by 1.25 equals 140, and we'll take the square root of that, and that's going to equal 11.8 meters per second. Okay, a small motor does 4,550 joules of work in 35 seconds. What's the power? Is another one of these. Power equals work over time, and they're giving us the work, they're giving us the time. So work here equals 4,550 joules. Time equals 35 seconds. And so we just plug it into that equation. So P equals 4550 divided by 35. 4550 divided by 35. We get 130 watts. Okay, you can run up a flight of steps in 20 seconds if your weight. So you're going to be lifting up your weight as you're going up. In the vertical height of 15, what's your power output? So work is force times distance. Power is work over time. We're going to plug that in for. We're going to plug the force times distance in for work. Well, let's see what we have to do. Let's go ahead and write down our givens list. So we have a time of 20 seconds. We have a weight, so that's going to be our force here. It's going to have to be lifted, 500 newtons. And we're going up a height. In this case, it's going to be a distance in this equation, 15 meters, and we're asked for power. So yes, we are going to have to take this, and we're going to plug it in for that. So power equals force times distance over time, which is the 500 times the distance of 15 over 20 seconds. So 500 times 15 equals 7,500 divided by 20. We get 375 watts of power. Okay, what height does a 2,000 kilogram mass have potential energy of 3 joules relative to the ground? So GPE equals mgh. So we have 3 joules. So GPE equals 3.0 joules. Our mass is 2,000.0 kilograms. And we're just asked for what height. So we have 3.0 equals 2,000.0 times 10 times h. So it's going to be h equals 3 divided by 2,000, add another 0 to the end because of that. So 2,000 times 10 is going to be 20,000. And this will be our answer. So 3 divided by 20,000. And you should get 1.5 times 10 to the negative 4th. And it would be meters because it's height. So that would be our answer to this question. Or you might have 0.00015. that would be the same answer as that right there. A 15 kilogram water balloon is dropped from a balcony. It strikes the ground with a speed of 20 meters per second. How high was the balcony? So back to the conservation of energy. PE initial plus KE initial equals PE final plus KE final. And what they're doing in their givens list, so you have givens right here. You have a mass of 15.0 kilograms. It's dropped from a balcony. We don't know how high the balcony is, but that's what it's asking you for. It strikes the ground, so the velocity or the height of the ground, height final is going to be 0. The velocity is going to be 20 meters per second. And now we're trying to find out how high the balcony was based on this information. So here you would have a V initial of 0 because it's dropped from the balcony. And so these are our givens going in. So we're going to have to break this down to potential energy, which is mass, gravity, height initial, plus kinetic energy, 1/2 mv squared initial equals mgh final plus 1/2 mv squared final. Now we can plug in all these numbers, 15 times the 10 times the height initial, which we're trying to solve for, plus the 1/2 times the 15 again, but this time it's not moving, so this is going to cancel itself out. And then we get to the ground, and the 15 kilogram object with the acceleration of 10 meters per second squared, and it's on the ground, so that cancels that self out, plus 1/2 times the 15 times the final velocity, which was 20, that's going to be squared. So now we're ready to do the math. So we get 150 hi right here, and that's going to be equal to 0.5 times 15 times 20, and the 20 is squared. So we get 3,000 over here when we put that together. So hi equals 3,000 divided by 150, and that's going to be equal to 20. So we have a height of 20 meters that this object was dropped from. Okay, so let's go ahead and keep on going through. Torque, the drawing represents a wrench. The left end of the wrench is attached to a bolt. 4 equal forces of 100 newtons are applied as indicated on the drawing. Which 100 Newton force would cause the most torque? So the most torque is going to be right here, because torque is force perpendicular times distance. This has no component. So this would be the least overall. This one's a lot shorter. So we want the most perpendicular, greatest perpendicular force, which would be that 100 is directly perpendicular, and we want the greatest distance. And so that, therefore, it's going to be C, which has both of those. Most perpendicular, which is, it's equal to A, and both of those are perpendicular, but it's going to be the greatest distance. And so that's what we're looking for. That's why it's C. Okay, what's torque at A? Torque at A, okay, so if we're doing the problem here, torque equals force times distance. And force perpendicular, they said, so it is the, it's going to be, the force here is going to be 100. And the distance here is going to be 0.12, which we see in the picture. So we have 100 there, and we got the 0.12 as our distance. And so our torque is going to be 0.12 times 100, or 12. And it's going to be 12, and it'll be newtons meters. Newtons times meters, and there's our torque here. What's the torque at C? The torque at C would be, so we're just going to do the same thing. We've got torque equals force times distance here, 100 newtons. No, not that one. Let me erase that. That's not our distance. We're looking at C right there. And so we have a force of C. It's 100. It's completely perpendicular, and that is 0.25 meters away. And so that's going to end up being 25 Newton meters of torque. Okay, what's the boy's weight in order for the seesaw to be in equilibrium? It's going to be F1d1 equals F2d2, and we have this 200 Newton girl, which is 6 meters away. This boy, we don't know his weight yet, but we know that he is 1.5 meters away. So F2 equals, when you plug this in, 200 times 6 divided by 1.5. So you divide 1.5 by both sides, and that's what it ends up being right here. And so 200 times 6 equals divided by 1.5, and I get 800 newtons. So this would be the boy's weight in this picture. Okay, you're a seesaw with a heavier friend. Where should you sit? Okay, so if your friend is heavier than you, anytime you're going to have that, if I'm trying to figure out where the fulcrum is going to be, well, so more force, less force, but you want to sit more distance away. So you can equal out the torques. You want to sit a further away, further distance away, so you can have more torque, because what you're doing is you're trying to increase the distance to make up for this. So the greater distance would be the reason, but it's because of this, because you want a greater distance because force is less. Okay, during practice, the student kicks a 0.40 kilogram soccer ball with a velocity of 8.5 meters per second to the south into a 0.15 kilogram bucket lying outside. The bucket travels with the ball after collision. So we're on to the conservation of momentum equations, elastic and inelastic collisions, as it's written on the equation sheet, but it's really just conservation of momentum. And here you have a soccer ball that's going to be kicked into a bucket. So that's going to go into the bucket, and afterwards it's going to be stuck in the bucket. So you're going to have the masses combined. And so we're going to have the inelastic equation, m1v1 plus m initial plus m2v2 initial equals, and we're going to have a combination of m1 plus m2, and it's going to travel with a single velocity here. So plug in all our information. You have a 0.4 kilogram soccer ball. There's our soccer ball. It has a velocity of 8.5 meters per second, and it's just a bucket lying outside, not doing anything. So it's going to have an initial velocity of 0. And when we add, when they stick together, their masses are going to add together. So the 0.4 plus the 0.15 will add together, and it's going to be traveling a final velocity that we'll be looking for. So we plug that in, 0.4 times 8.5 equals, and we get 3.4. And we want to divide the overall 0.55. So when you add those two together, that's going to be 0.55, and we get this answer. It should be the answer. So we had all the momentum, the 3.4, the 3.4 kilograms times meters per second of momentum was all in the soccer ball, but now it's going to have to be combined. So we expect it to be going slower. Let's find out how slow. So divided by 0.55, and we get a final velocity equals 6.18 meters per second. So it's sharing its momentum with the bucket, so therefore it's going to be less, which is what was expected. What is the decrease in kinetic energy during the collision? Okay, so let's find out what the decrease in kinetic energy is during the collision. So initial kinetic energy was, so initial KE was, we have from KE equals 1/2 mv squared. Initial kinetic energy was 1/2 times the mass, which was 0.40, times the velocity, 8.5 squared. And so that's 8.5 squared equals times 0.4 times 0.5. So we get, so our initial kinetic energy was 14.45 joules, and then afterwards, final kinetic energy was 1/2 times the mass combined was 0.55 times the final velocity, which was 6.18. So 6.18 has to be squared. 6.18 squared Let me make that look a little prettier. So 6.18 squared times 0.55 times 0.5, and we have 10.5 joules of kinetic energy. So that is the difference, decrease. And the decrease would be, if I wanted, so it says, what is the decrease? So I'm going to go ahead and say 14.45 minus 10.5